I will just leave the admission of new comers to you, okay?
Okay.
Okay, so I will start sharing the screen now.
So I am fulfilling my duties. I already admitted a person. And I'm switching off.
Okay, are you seeing my screen right now, or? Hello? Hello?
Yes, we are seeing your screen.
We do.
Okay,
Yes.
thank you. Because I'm using two monitors and well, that will be a learning path for me. So I hope everything goes okay. Okay, so it will be somehow the first part, I will, let's say, be speaking more. On the second part, I will be asking for your cooperation. So the first part, the first part is before the coffee break. I'm supposed to present you with some examples of NMR relaxometry and data analysis, part one. So this basically, for me, I will just present you a series of relaxation profiles and try to motivate you to the analysis that I will start explaining a little bit after on the second part. And Professor Danuta told you she will continue to explain how to approach this analysis of this type of data later on. Okay, so what do we mean by a dispersion profile? So we mean basically a representation of data of the spin lattice relaxation data that you have heard about yesterday as a function of frequency. So that's the term dispersion. That's where the term dispersion comes from. So it's a representation of data as a function of frequency. In this case, the Larmor frequency, which is proportional to the magnetic field that we are using in our NMR experiment. So in order to do that, I don't know how much of this you heard yesterday, but we need either one instrument that is able to perform the measurement of the spin lattice relaxation for different frequencies in a kind of practical and convenient way, or we have to use different experimental setups properly adjust to operate at fixed frequencies, and eventually we might need one equipment just to give us 1 point. But basically, in the end, all of them will provide you, when it comes to measuring the spin lattice relaxation, it will come out with a representation of data where your magnetization along the magnetic field. So usually we choose our frame of reference in such a way that our z-axis is parallel to the magnetic field. So this mz that I hope you are able to see my cursor moving. Actually, let me try to do a different thing. It's also one way to do it. Just 1 second. Are you still able to see my screen? Hello?
Yes, we can see your screen.
Yes, we can see.
Okay, so I'm using my remarkable tablet now to make a presentation, and I can just write things down. Okay, so this MZ here, let me choose a different color. Okay, red. Okay, so this MZ component here is parallel to the magnetic field. So we have a magnetic field, B naught, pointing up, and our z-axis is parallel to the, here not so much a vertical axis, parallel to B naught. And what we have is always this type of representation. So let me go here. Actually, the opposite. Okay, so this is what we had in this representation. I will show you how I got this. I'm showing here on the bottom the frequency. So this is the magnetization decay. So that shows the representation of the magnetization as a function of your tau. So the time you let your sample to relax in the low field. This is typical decay that you have in the field cycling experiment for a certain low magnetic field. In this case, the magnetic field that corresponds to 15 kilohertz. What I'm showing here is the fitting of the magnetization decay that we can get from the block equation. Just for you to remember from yesterday, I suppose you got this. So we really have to deal at some point with some mathematics. And in this case, there is a relaxation equation. So it's a differential equation that tells us how our Z component of the magnetization evolves over time. And we have this constant, this is relaxation time, the spin lattice relaxation time. And this equation, if you solve this equation, it will give a function which is basically, let me see if I'm not wrong with this. So let me see if I write it right. So if tau is 0, this is 1. So this is minus infinite that cancels this 1 minus infinite. And we are left with M0, which will be basically this value here. Actually, I'm showing this plot in a logarithmic scale. So tau 0 is something that in a logarithmic scale, it is pointing in this direction to the infinity. So I cannot represent it here in this plot. And M infinity will be the one that will be to this side. So roughly here in this value. So we have the magnetization that will evolve according to this exponential function. And we need to generate a profile, we need to obtain data for different frequencies. And this is basically what we have here. So I'm showing you a series of magnetization decays. Each one of them is fitted. You might be wonder what is this black curve and what is this constant and this green curve? What do they represent? So I write it down again. So if you look carefully, this is a function of tau. So again, M infinity plus M0 minus M infinity exponential over T1. And M infinity, this is the first term of this sum, is a constant. So it looks like this straight line, dashed red line. And the second component is an exponential function that decays. So this is the green curve that you see here. It doesn't look the familiar exponential decay that you might be familiar with, because this representation, this is a linear plot. So both scales are linear, and you have the traditional representation of the exponential function. Here in a linear logarithmic scale, you have this type of function. I mean, this type of line, this evolution of the green curve. And so you have a profile when you get enough magnetization decays for enough frequencies. There is a moment when the field cycling technique can be replaced by, or sometimes it's not a question of your choice, is a matter of technical possibilities. For high fields, you don't use field cycling anymore. You have to use the inversion recovery method as one of possible methods to measure the relaxation rate. So when it comes to this concept of inversion recovery, or let's say recovery, what it means is that instead of starting from a decay of the magnetization that comes from an initial value of the magnetization, M0, that is at a high value, and then we see the evolution to a low value, so we have a decay. Instead of that, we have a recovery. So it means that we start from a magnetization that has a lower value, and we observe how the magnetization evolves until it recovers to let's say, initial value, which is higher. So this is typical of conventional NMR setups and conventional of two techniques, which are usually known as either inversion recovery or saturation recovery. Well, this is some technical things that eventually you will see next week on the second half of this training school. So I'm getting to higher frequencies, higher and higher, and I think in this case, this profile was obtained for frequencies up to 300 megahertz. Sorry, one too many. 300 megahertz was the last point I investigated. Sorry? Hello? Okay, so perhaps you can try to check if your mics are muted, otherwise we can see can hear some noise eventually. Okay, so in this case, my highest frequency was 300 megahertz. Okay, so we have a profile, or we are able to follow how the magnetization decay evolves with frequency, and that now brings us to the examples that I prepared for you. Okay, so the profile I talked about already. Okay, so let's start with the most simple compound I came across with. This is tetramethylsilane, which is usually known as TMS. It's a compound that is used as in spectroscopy, NMR spectroscopy, as a simple compound to calibrate our frequency scale. Well, there's some technical aspects about this. I will not go into detail. So let's just see that this is a silicium atom connected with four methyl groups. So all protons in this rather spherical object are equivalent. And I'm representing the data that I told you about, this magnetization decay, how the relaxation rate depends on the frequency, so the dispersion profile. And as you see, for this compound, the relaxation rate here has a very low value. So it means that the T1 is very large. So of course, relaxation rate R1 is actually 1 over T1, or is equivalent to T1 minus 1. So this is the representation I'm using here. So a very small relaxation rate represents a very large T1. You might be wondering why there are no more points for these lower frequencies, and this is basically because in the field cycling, measuring very long T1s, this can be very stressful for the equipment, and sometimes we tend to avoid going into these problems. So the next compound I'm showing is N-hexane. So it's a slightly elongated molecule, just with carbons and hydrogens, a rod-like thing. You can find this same compound in a cycle, but this one was chosen to be rod-like. And the relaxation rate is slightly higher than the previous one and is rather flat. Now we move to dichloromethane, okay, DMSO. No, sorry, not the MSO. So it's also carbon, this times with 2 chlorines and 2 hydrogens, and the profile is still rather flat and shows here some small deviation that at some point we could consider within the experimental uncertainty that we might have in the experiment. But anyway, the values are systematically higher, the relaxation rate, I mean, than the previous compounds. So let's move to water. Okay, water, you might think, or sometimes you might wonder if it's the compound that has the longest T1, and you see by now that it is not. For water, we have about between 2.5 and 3 seconds, depends on the purity and the amount of oxygen dissolved or paramagnetic ions that might be, so the purity of our water. But typically, this is basically something between tap water and some deionized water. So this was some sample we analyzed. Okay, so let's move on. Dimethyl sulfoxide, so DMSO. So please remind me, this is sulfide, so this is sulfur, 2 carbon, 2 methyl groups, and oxygen there. Still a flat dispersion. So this is boring. You see, a lot of simple liquids have dispersions which are rather flat. Let's move to slightly longer molecule, still rod-like and still flat. Although here, again, in the high frequency, seems to be the relaxation rate decreasing a little bit. Moving to another, hexanoic acid. So it's also a elongated molecule, probably not as long as the previous one, the one seen, but this one has a polar group. I mean, there is some polarity in this terminal group, and we see a little bit better, at least we can perceive here slightly dispersion, slightly change with the frequency, very small still. Now we come to a slightly different compound. So instead of this rather simple, let's say, not so much, let's say, small molecules, we have a slightly longer one, and this time has a chain, which has a length which is not so much different from the previous ones, but this one has 2 benzene rings attached to it, and this is a very well-known compound from the liquid crystal community, and this is called 5CBs, a liquid crystal. So you might have heard about liquid crystals, actually the compounds that made possible all this revolution in display and screens that we nowadays use everywhere as a commodity. And for this compound, you see that in the isotropic phase, by the way, this compound, besides having isotropic phase as let's say, as the previous liquids, it has also in a crystal phase at a low temperature when it becomes crystal. So if there is an intermediate phase, which is called pneumatic phase. I will come to that in a moment. But in the isotropic phase, this is around 35, I mean, above 35 degrees, 40, 45, let's say above, as I said, 35, 36 degrees. It is isotropic, so it should look as the other simple liquids that I showed you before. And indeed, it is a flat dispersion with a slightly larger variation of the relaxation rate in the high frequency range. And if we now change the temperature on this compound, okay, so if you see the first one was for 317 K, and then I'm decreasing the temperature coming down to the room temperature. And you see, as I cool down the sample, the relaxation rate is increasing. Okay. And the interesting thing that I want to show at this point is that at high frequency, there is not much variation, but in the low frequency part, we see some change. It's clearly a change. And this last one in particular shows into this last low frequency in the kilohertz range. So this is 1 megahertz, this is 10 megahertz, and this is 10 kilohertz. So around the 10 kilohertz range, we see an increase in the relaxation rate. And this we are close now to this transition temperature that I mentioned before. And if I just move to the next one, I change the phase. So I change the material is no longer in an isotropic phase, it's still a fluid, but the molecules in this at this temperature, they show an alignment. They align themselves. So these molecules, if I represent them like this, they will show a common alignment. Okay, and this along one direction, which I call the director. Of course, from one, this if this a screen that I'm showing would be a plane in the liquid crystal sample, in this region, the molecules could have this direction. Sorry, let me do it better. Okay. In this place, the molecules will have copy. Okay, so in this area, the samples will have in this direction, but in this one, the direction could change. So the direction where the direction of alignment of the molecules can change from one region to the other in space, but the common feature it is that they are aligned. And the thing I want to show you. Okay, so let's forget about it. The thing that I want to show you is that by changing the phase, the profile changes. You see, I mean, it's obvious, I think, for you. The red stars completely change the shape, the way the profile looks. So looks like flat in this area and then decreases, and the red ones are, even the curvature of the dispersion profile is different, slightly different, okay? There is an inflection point here. So there is a curvature here like this, and then it becomes like that. Sorry about this, clear. Okay, so this is 5CB, and now for a same compound, the dispersion profile can change with temperature. Now, we go to a different type of systems. Let's go to water-based systems. And here I show some data of water in dextran. Dextran is some silica particles with sugar as well. Not silica particles, sorry, I apologize. With sugars, monosaccharides, disaccharides. I mean, I will not go into, I not will even try to explain you what dextran is, but it's something made with sugars. And the profile, it goes in the same dispersion, I mean, in the same range of relaxation rates, and looks like the previous one. So I will just come back, and next you will see the dispersion profile stays in the same area of this plot. And if I change temperature, I also observe differences in this system, okay? And this time, I'm showing, well, actually, I should have chosen the same variation of temperature. So here, let me go back. Instead of decreasing temperature, instead of decreasing temperature, I'm increasing temperature. So 295, 310, 327, 343. So when I increase the temperature, this relaxation profile comes down. So we could say, or we can say that the higher the temperature is, the more the system looks like a liquid. Or let's say this is a water-based system. So water, the profile that we observe, which is the behavior of water in these confined spaces, the dispersion that we get becomes closer to this dispersion of water that we have in bulk water. So water confined in narrow spaces produces some dispersion that goes away completely different from the bulk behavior. But this is interesting because if I now have water in cellulose acetate membrane, Ca cellulose acetate membrane with the silicium particles also there, or silicium atoms. The interesting is that, well, I found for one particular system in some particular conditions, I found that the dispersion profile, well, is not so much different than the one that we observed previous for a completely different system, this dextran. And this is a membrane used for nanofiltration. It is called asymmetric because the pores on one side of this membrane are larger than the size of the pores on the other side of the membrane. It's for, as I said, nanofiltration. And the dispersion profile that we get obviously corresponds to how the water behaves not only in the small pores, but also on the large pores. So it's a kind of average information that comes from the averaging all the contributions from water from all points in the sample. But nevertheless, the overall behavior is similar to the one that I showed you for Tecnico, which are the circles behind. Maybe someone that has the mic on. Hello? Are you still with me?
Yes, we are with you.
Okay, so please check your mics. So let's move on. So I can change the membranes. I can make the pores even narrower. And by confining more and more the water, more and more we change the dispersion profile that we get, okay? Meaning that the relaxation rate increases even more. So the T1 becomes smaller and smaller. But you see, the interesting that in high frequency, all these points, I didn't have the chance to measure for this. Please note, this is 100 megahertz here, and this is 300 megahertz, and this is 400 megahertz, and I could have measured at high frequencies. And I think you will agree with me that if I would measure at high frequencies, most probably these points will just go there eventually, okay? Okay, so water in confined spaces can, although is a simple molecule that in bulk has a completely flat dispersion, when in confinement, it shows a rather let's say, relevant dispersion. This is the same thing if we use water in silica particles. We also get, as with membranes, a dispersion profile that has, or as you can see, as, let's say, very similar inclination. So you see there's a slope here like that, okay? Okay, and what about natural products? For instance, cheese. There was a network that Professor Danuta was managing in the last years, and within this network we analyzed a lot of cheeses. And well, I'm showing here two examples. I don't want to tell you exactly what type of cheese is this, just to samples A and B, and just to show you that the dispersion profiles more or less stay in the same region where we just previously saw the dispersion profiles of water confined in spaces. Of course, for cheese, There is water, of course. There is some of these cheeses were not completely dry. They have always some moisture. And of course, there are some small molecules that also behave. They are small, so they move eventually. They have some mobility, so it's not a completely solid, or it's a viscous system. We could call it a nanocomposite in some sense, because there's a mixture of compounds packed together, and some spaces can be, I mean, there is some spaces where small molecules can still move. And probably this is what we are observing here. So the mobility of the small species confined in these narrow spaces. And here, the highest one that we have is for these pectin gels, pectin-based gels, so sugars, and we have a very, let's say, pronounced dispersion. Okay, I've shown several examples of dispersion profiles for different compounds, and I showed you examples of, let's say, how a simple molecule, in that particular case, water, confined in spaces. But we can have other types of systems where we can observe some interesting dispersions by mixing different compounds, or taking a simple compound such as water, or let's not call it simple, a typical liquid like water, and we put a little bit of manganese chloride, so a paramagnetic ion. And just a small concentration of this paramagnetic ion changes the dispersion profile. So we have water, and water with a little bit of manganese chloride shows a dispersion profile that, as you see, goes in the region of where we previously observed all these interesting dispersions in these more complex liquids. So as you can see in this frame of reference that I'm having here, so a plot that comes from -0.01 to 1,000, and from I don't know, something like 2 kilowatts to maybe 900 megahertz. Within this observation area, we see all the profiles coming inside, and they are show or evidence features that are more or less common to each other. In the high frequency range, they all come down here, or most of them come down to the place where we find the simple liquids. And in the low frequency part, for lots of systems, we see the relaxation rate increasing. Now, this is again for water and manganese chloride. So let's move on. Here, I left in gray the previous two cases, water here and water with manganese chloride, and now I'm showing a completely different compound. It's an ionic liquid called an ammonium ionic liquid called typically its common name is aliquat. So here we see some aliquat, or some representation of molecules packing. This is part of a study. So there's a nitrogen atom here and some long chains and a smaller chain, and these molecules kind of pack together, but they produce a dispersion profile that the funny thing is that it kind of falls in the same area where we find the manganese chloride and the water, the solution. So there is no relation between these two systems, but the profile stays in the same place. So there is no way, by looking at the value of T1 at any given frequency and guessing what the compound might be. So this is I will not call it a problem of field cycling, not being able to tell what the compound is by measuring a single T1. Eventually, you can say something about the compounds by looking at the complete profile, but we have to be careful also, because you see here, these two profiles are not so much different to, in a crude analysis, at first approach, and well, they are completely different systems. Okay, so even let's go for more. Okay, so let me show you now a little bit more composition. Let's say I now have DMSO, so I bring back the dispersion profile I showed you for this dimethyl sulfoxide, the DMSO, and I show you again now this red squares is the same aliquot that I showed in blue, but mixed with a little bit of the MSO, 10% in weight. And you see, well, there's not much difference. I mean, in the high frequency, almost no difference at all. And in the low frequency part, a small difference is only observed. So I put a little bit of the MSO in aliquot, and it doesn't show much difference. So yeah, that's it. But now I put a little bit of iron chlorine in this system. So I put some paramagnetic ion in this system. So the iron here plays the same role as the manganese in the previous example. And I'm now, and we remember, I removed the curves here. No, they are still here. So this is water, and here behind is the water with manganese chlorine, okay? And here now on black is the aliquot with, in molar concentration, much more iron than what we had in what I showed in the previous data for manganese. There was 2 millimolar of manganese, and here is 12 millimolar of iron, chlorine. And you see, with respect with the blue empty squares, the dispersion is pretty much the same in the low frequency range, but it's a large bump here, large dispersion. I mean, there's a change here, dramatic change. And the interesting point is that, remember, when I mixed a little bit of the MSO with aliquot, almost no difference at all in the dispersion. But if I put the same amount of the MSO in the system that has aliquot and iron, then there is a change. So there is a, let's say, reasonable, we can observe, it's an interesting change. Even making more, or enhancing even more this additional, this change in the relaxation profile in the enhancement in relaxation rate in this profile. By the way, this is one feature. This is increase. Let's say the relaxation rate is either flat or decreases when we go from low frequency to the high frequency, and then in this, let's say around 10 megahertz or slightly below, let's say above 1 megahertz, this increase in relaxation rate is can be considered, I would say, a signature of the presence of paramagnetic species in your system. So this is what we call usually paramagnetic relaxation enhancement. So the relaxation is enhanced, it increases as a result of the presence of these paramagnetic ions in the systems. All this data was collected from a bunch of papers that you find. I mean, later I can share that with you, and you can observe them. I mean, from the representation of data point of view, this is what I had prepared for you. I can, before going into a coffee break, if you don't mind, I can now start to, let's say, let you a little bit of a glimpse of what will follow. I will show you now all the data I collected in the same plot. Just 1 second. Well, it's boring, I suppose. I could have prepared this. Are you still with me?
Yes, we are.
Yes.
Any curiosity? Any questions? It's much more interesting if you talk with me, because otherwise I feel that I'm alone. Lots of data I collected for this. But I think in the end, what I want you to take back to understand, I will try to summarize in a moment. Oh. Okay. I will have to create here some button to make this all available. Okay, show. Well, maybe if I don't show them all, it doesn't matter at all. But well, I'm getting there. Okay, so show. Okay, you see lots of systems. The relaxation dispersions, they all fall within this range. The range of the accessible by both field cycling NMR and conventional NMR. Do not, please note that nowadays the most recent stellar machines, equipment is able to cover pretty much the frequency range that I'm showing here, perhaps not the points at 300 and 400 megahertz, but I think the most recent machines go to frequencies of 100 megahertz or even more. And in the low frequency part, well, typically we work above 10 kilohertz, but I didn't show you data that goes down to one kilohertz or even below. But it's possible to make field cycle measurements at these frequencies. We just have to compensate well the Earth field and any other fields or artificial artifact that might show at this low frequency range. But and with respect to the relaxation rate accessible, I showed you from this TMS, which has a very small relaxation rate, to relaxation rates about 1,000. You see all the dispersion profiles fall here. And the challenge now is to be able to say, to use this data to characterize the system, knowing that by the profile alone, by the shape, is not easy to make sure that we are on the presence of a particular system, because we can find another system entirely different that has a dispersion profile that is not so much different. And the question now is, can we really say something about the system in spite of these similarities and dispersion profiles? And that's the topic of, I will start talking about this in the next session, and Danuta will continue with that later on. So, questions?
I think there is a question on the chat. If you may be able to read it.
Okay. You don't want to speak. Okay. Okay. There's a question about the possibility of being bi-exponential. I will just come to that in the second part. Yes, of course, we can try. We can check, and I will address this in a couple of minutes. But if it's a bi-exponential, then we have to deal with that, and it might be, sorry, bi-exponential, 3 exponential, and in some cases when it comes to polymers and polydispersed systems, or natural compounds, better said, it might happen. Let's say oil, crude oil is a nice example of this. You don't have just one exponential, not the two, not three. You have a completely distribution of exponentials. It can be a rather complex system where you need much more than one exponential to explain your data. And from the point of view of discussing the relaxation rate profiles, is a challenge indeed, because the interpretation becomes harder, because it's harder to assign, or might be harder to assign one particular component or one particular value of the relaxation, or one, let's say, if we are in the presence of a bioexponential decay, it means we have two T1s, and we have probably a mixing factor in this between these two exponential contributions, and we have two T1s. Okay, we can say I make a representation of one of the T1s as a function of frequency, and I make another plot with the second relaxation time or rate as a function of frequency. So I have two profiles. The question is, the first question is the mixing factor constant for all the magnetization decays, or was the mixing factor free when you made the analysis? And just this is the first question, and then depending on the answer or depending on your assumptions, then the discussion of the data. And then if you have two components, does this means that you have two spin populations that do not communicate with each other, so they are completely independent populations, and the amount of spins in these different areas does not change, and does not show any behavior that for some coincidence, for some reason, produces a relaxation rate that overlaps somehow, or there is a, let's say, is a porous system where, in spite of the, let's say, the most mobile compound is in one particular area, but is nevertheless able to diffuse slowly to another compartment, and then you have an homogenization of T1. So there is what we call spin diffusion. So all the in this case hydrogen. So all the hydrogen nuclei will be communicating all the atoms through dipolar interaction, and there will be a common relaxation of all the system to the network. Another question. Yeah, okay, so this manipulation of the data, which which I show you here just to compile the data. I mean, in a moment I will show you this platform where you can play with it. Okay, the platform here is just an accessory. Okay, you can do that with whatever software you choose to use. It's a matter of how much time you invest in making the thing work. More questions? No dialogues. I suppose this was, I mean, it took me about 1 hour, right?
Yes.
Okay, so do you want me to move on, to make the break now? I can continue a little bit.
Actually, according to the schedule, you are supposed to continue.
Okay.
And then we will have a longer break, like half of hour, but of course we are pretty much flexible and we can do whatever we like.
Okay, then let's move on. Okay, so it seems that no one is willing to have a dialogue, but okay, but perhaps some of you wish to try. Okay, so in order for me to explain a little bit more about, let's say, introduce you to the data analysis, the way we do it, or even to explain how this representation that I'm using here using the browser, how it works, how this FITEA works, the first thing that I might do is to invite you to try yourself. So I just, let me open a new window and invite you, each one of you, to go to FITEA.org, and then you just register and you will be able to follow. Perhaps I give you, I can, let's say, show you the first steps. So you just choose register. You are still able to see my screen, right?
Yes,
Yes, we can see.
Okay, so I choose register and well, okay, let's start then. The main web page has some, let's say, some information. So, and then you can move on to register. Okay, in register you can find two servers. If you register in one, you will be registering also on the other. So they share the information, but you can choose one. So if you choose one, the registration process is a straightforward thing. You just have to type a valid email and then sign up. Okay, I can do it myself, but I will not complete the process. Okay, let me say new FITEA user. Okay, sign up. Okay, so you are asked with a question that is supposed to prove that this is not a bot, not an automatic not an automatic program interacting with this. So you are asking.
Oh, sorry. What happened if actually the chatbot would speak out?
Okay, I mean, yeah, the chatbot. Yeah, I'm wondering. I'm curious. I don't know. I have to. I will make this try. Now that you ask me, I will make a copy of. I will grab this image here, and you know there is this new version of ChatGPT, and
yes.
also the Google version are able to interpret images. So I will put this there and check if he's able to figure out that I'm expecting a number and then clicking on email password. I don't know, maybe he's able to do it. But one thing these bots, this ChatGPT and also the other one are not able to do yet, I think, not the commercial versions, is that they are not able to actually type here the numbers. Not the commercial versions, okay? The ones that they are working with, yes, they are able to take action. So just make, I mean, it will be able to just put here the right answer and proceed with the proceed. But I think that ChatGPT, the version that we can have access to, and also the other one, I don't know, it was Bard, but now it's no longer Bard. So I don't know the name of the Google version. They will probably find the answer. Sorry?
It's Gemini now.
Sorry?
It's Gemini now.
Yes, right. I think they will be able to interpret. Maybe they will figure out what is expected. But I think they will not be able to type. So there will be no actually automatic registration. But it might happen. So this was, this FITEA comes from 2009, and in 2009, I was pretty sure that no robot was able to answer this. Nowadays, I'm not so sure. Okay, anyway, If you give the right answer, and I don't know what the right answer might be for you, you have just to type email password, and you should get an email with a password. That password might be actually an empty field. In that case, in the following process, in the following step, I'm sorry, if the password is blank, you use blank as old password, and you can set your own password, and then you are ready to go. Okay. Is anyone trying? I could see, let me see if I'm able to check if some of you are trying to do it or not. Okay, not many people, I think. Well, it doesn't matter, so I can continue. Do you want me to continue, or are you trying and it takes longer? Okay, Ricardo is logged. Okay. Okay, so for those of you that don't want to do it right now or are not interested in, and eventually if you come interested later, there is some support and there are some videos available, and actually Muhammad, which is in the audience, is going to prepare I have a series of videos, but they are in Portuguese. So someone will have to translate that to English, and Muhammad, I think, will do that. So eventually, in a couple of months, they will be available also in English. But you can have this, can look for that later. Not sure. Let me check. I'm giving you some time. Okay. So let me log in. Okay, I also created a kind of user with a different email, and I logged in as this new Fitea user. So for those of you that are trying to log in to register, if you compare what you get once you are logged in, if you compare what you see with what I'm showing on the screen, you will see some differences. And the differences are that you will have probably I hope, two folders, two lines alone with tutorial 1 and tutorial NMR. And here you see on the screen that I have other lines. And actually, each one of these lines corresponds to a folder. You can check that if you have this. Okay, so Ricardo has the tutorial and tutorial NMR, so it's okay. So that's the default. And actually, even if you delete these folders, the next time you log in, you will get them back. Okay, they are always there. They are kind of starting point of all that. After the folder here on the screen, you have manage and browse, and let's see browse. If you browse, you will see the contents of the folder. Lots of files, some of them, the names have a meaning, and if you dig a little bit, if you investigate a little bit, they will become, you will figure out what they are for and the purpose. But basically, is a folder, and there is another folder which is called fit. And in this fit, you have also lots of files. The number of files changes with time and depends on what you do. And actually, the most important files in these folders are these names that have this SAV extension in the name, and also the files that have PLT. SAV are for the fits, and PLT are for the plots. I will show you in a couple of minutes. So these are the files that are eventually necessary to preserve. All the other files are temporary and actually could be deleted because they are created every time you do something. So that's browse. In manage, let me check, for instance, manage here. In manage, you have a different perspective of the contents of the folder because you still are presented with the files. The files now can be, you have the folder name and the file name, and you are able to select which files you might wish to delete. And if you come down, you can delete the files you selected. It will tell you that the files were deleted. And well, this is a way to clean your area. Okay. You can, of course, you can delete the complete folder. Like I have this folder here. It's called trash. In Portuguese, lixo is trash. I don't know what's the content in trash. Some things. And I could, because it's trash, I can, I can come here and in manage, I can delete the whole folder. This is this special box that if I tick on it, it selects the entire folder. And if I delete selected, it's gone. The whole folder is gone, okay? If you delete something like I did, a complete folder or even a file, there is still a good chance that is not completely lost, not in the sense that you cannot never recover it. Because, as I said, there are two systems, that is this two machines, in two different locations, and they are sharing the information with a delay of about 2 minutes. Let's say 1 minute in each syncing in both directions every minute. So I think you understand. A goes to B and B comes to A, and every 2 minutes this is repeated. And every day there is also a backup being made to another hard drive, another disk in a third location. So eventually this data is secured, so more or less. Okay, so this is a little bit the story of the folders. Now, let me introduce let's say, the folder that is not so much devoted to NMR, and then we'll concentrate on the NMR. So the one that is called tutorial 1, if you click on it, you have plenty of examples of data that it's possible to use to analyze. And when you click on the folder that I did in tutorial 1, you see that it's tutorial 1 here, the name of a folder, and this will be the name of your, let's call it fitting project, or let's say what you want to do. And when we do that, we see this web page, and it contains the 3 things that you probably will have to do, or will have to consider. Whatever software you might wish to use, you will have to do these 3 things. You have to use or put your data somewhere. Here is a text box where I can type numbers. Okay, 1, 2, 3. And you have to set or let's say choose how your data is represented. So you have to define your plot parameters, like the axis, the labels, the values of minimum and maximum values, all these things. Of course, in a graphical interface, most of these settings are somehow hidden, because if you want to choose how for instance, the axis here looks like, you just click on the line, and the line opens a menu, and on that menu you'll find this type of settings to choose from. In this case here, you have them explicitly shown, but this information must be there in the system for you to be able to see your data properly. The third part is obviously the function that you will be fitting to your data. And pretty much it summarizes also what you need, because you have obviously to define the name of your independent variable. Here in this example is X. You have to define your dependent variable. Here I choose Y, and you have to define both the function, so the equation, the expression that will just be used to as a theoretical model, and to identify the names of the fitting parameters. So these 3 things are always present, whatever the software is. They are more or less obvious, they are more or less evident on the screen, but they are there nevertheless. Here in this case, in the case of Fitea, you are shown, I mean, when you open the interface, you see this. And one thing here that I might introduce now is that below this text box where you are supposed to put your data, please note that the data here is presented in the form of 3 columns with the value of X, the first column. Sorry, I cannot choose the column alone. The second column has the value of Y. So this is the independent variable. This is the dependent variable. And here is the uncertainty of the dependent variable. And every line that starts with the hash is a comment line, is something that will not be considered in the calculations. And here below, there's a second text box. It is a sort of calculator. So I can make calculations with the data. It can be handy if you want to do things to all the data at the same time. Let's say I want to change the order of the columns. Okay. C3, C1, C2. Okay. And calculate, and I change the order of the columns. Okay. But I can do other things. I can do now. I have to get back. So C2, C3, C1. But I have C2 times 2, C3 divided by 10, and C1 also divided, so multiplied by 0.5. Okay, so the first line, I will change the order of columns back to what it was before. And on the second one, sorry, I will multiply the first column. I will multiply after this process, column number 2, this column will be placed on as the first one. So this one here is C2. After the first step, it will be C1. So I will be multiplying that C1 by 2. And the same thing for the others. So, okay, so I multiplied. I mean, you can repeat the process if you wish, one by one. But this is a calculator that you can make some, complex computation. You can even add more columns. The other thing, one advantage of this is that, well, I made a mistake and I didn't want to make this calculation. So no worries. I can go back with the backwards button in your browser, and you recover immediately what you had before. Even if you close this tab by accident, I can go back to history, and I can reopen the last closed tab, and I get it back. So it can be handy. I mean, it is handy to play with this, having a browser, working with a browser for this purpose. So let me get back this C2, C3, C1. Are you still there? Those of you that
here.
Okay, those
Yes,
of
we
you
are
that
here.
are trying, are you, is it working for you? I mean, are you able to reproduce more or less what I'm doing?
Yes, we are.
Okay, so this is basic things that you can do. Now there is this is the basic. It's by default you select basic. This is the basic default. This is the entry point of the system. But you can have you can have other levels, like you can use this to perform more complex data analysis. So it can be advanced, or it can be expert, or you can be master. Okay, the master actually is not, the word does not represent exactly what you have to be. It represents only the flexibility of the system. In the master mode, you can have all the flexibility available in the system in one layout. Then there is a calculator. The calculator I will show you in a moment. Okay, but let's see. I have this data, I have this function, I have these fitting parameters, and I have these plot settings, and I can do two things. I can, more than two things actually. I can just data plot, and it just plots the data. It does nothing else, just plots the data according to the plot settings. You can, let's go back, you can instead fit or plot. Okay, well, fit, I think you can anticipate what we'll do. And what about plot? Well, probably it will can anticipate what we will do as well. But the two things are slightly different, because if you plot it will just draw your curve, your function, using these values for the parameters, and it will just plot your data and plot your curve with these parameters. If you fit, it will try to find the values of the parameters, A and B, that minimize the chi-square. I'm not sure if you ever talked about the least square minimization or the minimization of the least squares. Did you ever heard about this? Did you ever hear about this? Maybe not, or maybe yes. Anyone? No? Yes? Hello? Okay.
We are done, definitely.
Okay. Let me see if I have still, close, no sharing, no longer sharing. Let me see if I'm able to share again. Did you introduce that, Adam? Or someone
No,
else?
I
No?
didn't introduce this.
Okay. So, well, it's not so much relevant, but I think it's worth, it compensates if you should be sharing the screen. Sorry. Connect to the app. Okay, sorry guys. I have to start Remarkable. Now it shows. Okay. So sharing, let me see if it accepts. No? Okay. Okay, so what I mean is that I have okay, so a brief introduction to this. I assume a bunch of experimental points, which I'm drawing here with some uncertainty. Okay, might be the same for all of them or different, and obviously there is a scale here for the x-axis and the scale for the y-axis. And the question is, if I have a function, how can I fit, what is the meaning of fitting the function to the experimental points? So if I imagine as one of the most simple expressions possible, if I imagine a straight line, a plus bx, this means actually finding the value of a, which is the value at origin, and b, which is the slope, and this a, if it's 0 and 0, a is the value of the function at origin, and b is the slope of this line. Okay, and the question is this straight line that I draw here the best line that I can figure out, that I can imagine, that fits my data? And I think you all agree that this one that I draw is not the best one. Obvious, right? If I draw another one, I can do it better. Probably this one is better. You will agree with me. But is it really the best one I can draw or not? It's a slightly harder problem, because then I have to do that in a kind of numerical way, or find a numerical way to do it. Otherwise, I will have always doubts about am I choosing the right one or not? So one way to do that numerically is by minimizing the sum of the differences of the squares. What does it mean? It means basically calculating a sum which calculates the difference between the value of the experimental, or the experimental value for a point with order I minus the value of the, the value of the theoretical curve for the same position. And eventually we can give some weights. We can say that this difference, the importance of this difference is weighted with respect to the uncertainty of the experimental point. And I do that to the square. So what does this do? It's actually calculating this difference here, this difference here, and this difference here. So this difference. Let me put a point which is rather bad, this point. So this will be the difference here being calculated. So the difference between the experimental point, this, and the theoretical point, that. So this difference. So I'm calculating this difference and making a sum of them. And I'm using the square because, you know, this point is below the curve. So the theoretical curve is larger than the point. So this difference is negative. But for this point, the difference, the experimental point is larger than the theoretical point, which is smaller. So for this particular point, this difference is positive. So I must not take the risk of getting a sum equal to 0, because 0 means basically that there will be as many points up or as many positive differences as negative differences, the sum is 0. And that is erroneous. So I'm using the square to make sure that all these differences count as positive for this sum. And now I minimize this number. I minimize this function, actually. This is actually a function of what? Of the unknowns. And what are the unknowns? Well, I know because I measured the experimental point, so I know this. I measured, or I assumed, the value of x because this is the position that I choose for every point. So I know x and I know y experimentally, and this is the experimental. And what I don't know is a and b. So this is actually a function of a and b. And well, I told you we have to minimize the chi-square. So basically, we have to be able to find a way to minimize a function. So if you go back to Math 101, you will find out that the first condition you need to fulfill is that you have to make a partial derivative, which I will not bother or even try to explain you, but basically you have to solve two equations. So you have to differentiate this function f with respect to a, differentiate with respect to b, make them equal to 0, and that eventually will lead you, if you solve properly the equation, the values of a and b that are able to minimize this function. This only happens because we are using the square. So we are, let's say, pretty sure that the Jacobian or the determinant of the Jacobian is positive. Well, this is a mathematical technicality, but nevertheless, if we are working with the square of the function, with a function which has the squares, just making the partial derivatives equal to 0 makes the system, give us a system of equations that once we solved it, we get a and b. This is very simple or straightforward for this function, which is a function that is linear on the parameters a and b, but can be a rather difficult task if the function is not linear on the parameters. If you are wondering what this means, I tell you, if you remember, I wrote you here the expression for the magnetization decay. Okay, so for this magnetization decay, what would be what are the parameters? Well, in this case, this is a parameter, a fitting one. This one is a parameter, and T1 is a parameter. So this is a parameter. So we have three parameters. These ones are linear, so the function is linear on this both M-infinitive and M0, but is non-linear on T1 because it's part of the exponent of this exponential function. So calculating, for this case, I would have to calculate the chi-square to the respect of M-infinity, calculate the chi-square with respect to M0, and furthermore, calculate the chi-square with respect of T1. And make them all equal to 0. So it's a system with three equations and three unknowns. And solving this does not lead us to we cannot solve this analytically. So it's difficult. Sometimes for this particular type of expressions, there is a way around. You might have found that, or someone might have explained you that. Because you can say, well, but what happens if I actually know the M-infinity? Well, in that case, I can make a trick. I can use a trick. I can make mz minus M-infinity, and this will be M0 minus M-infinity exponential minus t over t1. And I can apply logarithms, so I can make logarithm of mz minus M-infinity is equal to logarithm of M0 minus M-infinity plus, actually, in this case, minus tau over t1. Oh, but that is interesting because now this, if I call this y, if I call this a, and if I called b to 1 over t1, I will have my equation, sorry, which now is a linear equation. And then I can make this my life easier in this way. Yeah, this is true. This is a way around making the fitting of an exponential function slightly less harder by applying logarithms to this expression and linearizing the function that I will be fitting. So here, instead of getting M0 minus M-infinity, we will get the logarithm of M0 minus M-infinity. And instead of T1, we will get B, which is the inverse of T1, actually the relaxation rate, or minus 1 over T1. Okay, so these are tricks that you can use to make your life easier when it comes to fit your data. Anyway, so fitting the data means finding the parameters that makes the line, the theoretical curve, come close to your point. So let's try. Okay, I'm fitting A and B. So if you try, you should get something like this. Okay, yeah, someone on the chat says that it uses MATLAB. Yeah, it's obvious. You can do most of everything that I'm doing here, you can do with MATLAB. With more or less effort, you will get, I hope, exactly the same results. So it's basically a choice of yours to the software you use. Okay, so you have A and B, and yeah, you have the coefficients A and B. Okay, so I told you that we are minimizing the chi-square or this q-square, and I will be able to show you. So there is below this plot that is generated automatically, there is a series of links to several files that we might find interesting. One of them is this fit log. The fit log contains, a report of all the things that were made. And one thing that I should point is that the actually numerical minimization of the chi-square is done by this numerical routine, min-wee, which is part of the CERN library of the numerical functions, numerical routines. And it has different methods of minimization. It has this simplex method, it has a scan method, and this scan method is rather interesting because it shows how the Q-square, which is represented here in the vertical axis, changes with a given parameter. So here is how the Q-square changes with A. And you see the chi-square goes down to a minimum, goes up. So actually this is the A that makes the Q-square minimum. And for B, you have exactly the same. So indeed, this method, and obviously all the other methods that this min-we uses, will contribute to get you the best values of A and B to minimize your Q-square. So this is how it works, and it shows here the fitting curve. Now, this fitting curve is actually a combination of two components. A, which is a constant, and Bx, which is a straight line that runs through origin. So I can take advantage of this small suggestion here below and put a backslash before my plus and compile the function again. And when I compile it, I see two other lines. You should see two other lines here, and you have the ability to change the line types and the colors. And I suggest you to do that because it will be interesting. And actually you saw already, I showed you already what it does. So I don't have now to make any fit because I made already a fit. It gave me already what I hope to be the best values of A and B to minimize the chi-square. I can just make a plot. And now I make a plot using these numbers. And what I get is now the black curve is the same as before. And now we are presented with two additional lines, the red and the blue, and they represent the two contributions of my function, the constant A, which is the horizontal line, and this straight line that runs through origin. So this, I see the components of a straight line. This is a kind of, not very interesting thing to do for a straight line. Well, you might find surprising that sometimes it's nice to see even for a straight line, but it's much more relevant when it comes for the NMR relaxation. Okay, perhaps this is a good. What about time? We should have a break now, right? Hello?
Yes, we should have a break.
Okay.
And actually, this was quite long. Yeah, what we thank you a lot, really. I think you're just tired, so maybe we could take a longer break than anticipated.
Okay.
Because we are supposed to have let me check. We are supposed to have a break until 11, and then you have next 1.5 hours, but maybe we could have break until, I don't know, 11:15.
Okay, it's no problem for me.
I mean, it's up to you.
No, it's okay. It's okay. I mean,
I just hope that you are tired.
Okay, I mean, it's okay, actually. I can continue. Of course, it will be nice to make a break now. I need to drink some water. It's more about the audience, if they want to relax a little bit longer or less. So if some of you wishes to say something, it would be nice, because 11:15 is okay for me.
So 11:15 or 11, dear audience. So quarter past.
Quarter past 11 it is. Okay. Okay. Okay, I will stop recording then, and we will. Or did you stop recording already? I'm not sure.
I did not.
Okay, so I will stop recording. Let me see how to do that.
Okay, because it will be, like half of hour now, more or less. So I think people need that.
Okay then.
Quarter past 11.
Yeah, sure. See you in a couple of in 45 minutes. Okay.
Okay.
Okay. Thank you. Bye.